Welcome, everybody. Before we're ready to see how physics leads to God, we have to lay down some foundations and learn a little bit of physics. Aaron, please tell us the main topic of discussion for today.
Sure. When probing the universe at its most fundamental levels, physicists have discovered many constants of nature which present a major challenge to their pursuit of a theory of everything.
Whoa, Aaron. I thought we agreed you were going to keep it simple. That's not simple. Nobody knows what you're even talking about.
So why don't you say it? But you also remember, Ellie, not too simple.
What Aaron means is that our universe is built on approximately 25 crazy numbers, which seem almost impossible to explain. And these numbers create a great mystery which drives physicists crazy. Is that okay, Aaron?
Yeah, that's pretty good. I'm Rabbi Aaron Zimmer, and today we'll begin to see how the mystery of the constants directs us on a journey which leads from physics to God.
And I'm Rabbi Dr. Eli Fader, and today I'll simplify, in more common terms, Aaron's explanations of the physics. This means that I'll take some of his more complicated statements, create analogies to help you understand them, and translate them into plain English so you can understand them too. Welcome to Physics to God. Welcome. This is Physics to God, a guided journey through modern physics to discover God. My name is Eli Fader, and I'm an Orthodox rabbi and a mathematician.
And my name is Aaron Zimmer. I'm also an Orthodox rabbi with a deep interest in physics and philosophy. On this podcast, we'll discuss some of the most fascinating developments in physics and make a convincing argument that they point directly to the existence of God.
We'll get to the fun in just a minute, but remember to subscribe to Physics to God so that you don't miss an episode. Write a review or share it with any of your friends who are interested in science and God. If you have any comments or questions, check us out on Facebook or email us at physicstogod@gmail.com. Aaron, while I was tough on you before, I do think you opened with a good summary of what we're going to discuss today. However, I think we all need to hear it once again, this time slowly, and then unpack it one step at a time.
Sounds good. Here it is. When examining the universe at its most fundamental levels, physicists have discovered many constants of nature which present a major challenge to their pursuit of a theory of everything.
Okay, got it. As I see it, you mentioned four things that we should really take one at a time. First of all, you mentioned the idea of fundamental physics. Secondly, you mentioned constants of nature. Third, you've talked about a theory of everything. And finally, why the constants of nature present a major challenge to physicists finding a theory of everything. Let's take these up one at a time. First of all, could you tell us a little bit about fundamental physics, what that means, what it is?
Fundamental is a word that we're going to use over and over in this first episode. So let's get clear what it means. Fundamental means the most basic thing, something that's irreducible. It can't be broken down and explained in terms of anything else. And there's a reason why we say physics is the most fundamental of the sciences. When scientists look at the world, they see a plethora of diverse objects in the universe. They see stars and planets and life, and they try to explain those things, make sense of them, find some order in them. When scientists study living organisms, they realize that those organisms are made up of cells, and those cells are made up of different types of molecules. And those molecules are made up of atoms, and those atoms are made up of particles. And once you get down to the most basic particles, you can't go any further. Those are the fundamental particles that physics studies. So in a sense, you go from biology, explaining it in terms of chemistry, and chemistry is explained in terms of physics. And the basis of everything is physics because there's nothing more basic than it, nothing more fundamental than physics. And physics, in a sense, explains chemistry and where you get all the different molecules and elements from, gold and silver and hydrogen and helium. And in a sense, chemistry explains where you get life from. By combining all these molecules into proteins and lipids and carbohydrates, you end up with all the different components of living cells, and putting cells together, you get life, and you end up with biology. So that's what we mean by fundamental physics. It's the bottom or the base of the scientific explanation of all the diverse things in the world. So by physics discovering what the fundamental particles of the universe are, like electrons that are parts of atoms, or photons, which are the smallest little parts that make up light that we see, it's able to explain all the world around us.
Correct. When you do that, it's not only for life. That's also the case when it comes to other things in our universe. For instance, stars. When you break down stars, you end up realizing that those too are made of molecules. And you could study those molecules by chemistry. And then you could break those down and realize that they're also comprised of fundamental particles. And the idea is that everything in the universe, ultimately, if you break it down simpler and simpler, you end up getting to physics. And at the core of physics lies fundamental physics. Let me give you an analogy. Imagine you have a city which has buildings and bridges and waterways, cars. And then when you look closer at the city, you realize that the city is actually made out of little Lego pieces, building blocks, if you will. And these Lego pieces are different colors, different sizes, different weights. And the idea is that all the complexity that we see in this city is really just different combinations of all these small little Lego pieces. In that sense, you can imagine the universe is like that city, and the fundamental particles are really like these little Lego pieces. The only difference is that our universe is much, much more complex than one small city. It contains so much more richness than our one little city. And also, the fundamental particles are so much simpler, so much smaller, so much more basic than these Lego pieces. The Lego pieces themselves are made out of billions of fundamental particles.
Besides physics studying these fundamental particles, it also studies the laws that govern how these particles interact. So if we have two fundamental particles, like an electron and a photon, what are the rules that govern their interaction? Those rules are called the fundamental laws of physics. If we put together all the basic particles of the universe and the laws by which they interact, we get something called quantum mechanics. The other fundamental law of physics is called general relativity, which teaches us about space and time and sets up the whole framework in which these particles interact.
Carrying the Lego analogy a step further, we could discuss laws about how the different pieces fit together. For example, maybe the yellows attach to the blue and the reds can't possibly attach because they don't fit. And the idea is that we could have laws within the city. If you're building the city out of Lego, you could formulate laws about the interactions, about which Lego pieces fit with others and how these pieces fit together. That would be like analogous to how quantum mechanics teaches us about the interaction between the fundamental particles. Furthermore, as an analogy for general relativity, we could consider the shape of the surface on which these Lego pieces are built. Is it a flat surface which they're being built? Are there hills or mountains? And the properties of that surface tell us something else about the city. Similarly, the general relativity tells us about the space in which the laws of quantum mechanics apply, in which the fundamental particles interact according to the laws of quantum mechanics. Aaron, maybe you could tell us now about the second topic which we have to discuss today, which is constants of nature. What are these constants of nature?
Okay. The thing to realize about these particles is that there's a qualitative component to them and a quantitative component to them. What I mean by that is, let's take an electron. An electron has properties, qualitative properties. Its mass and its charge are the two most important properties for us to think about. So its mass on a qualitative level means that an electron is heavy. You put it on a scale, it weighs something. The charge of an electron tells us that it interacts with light. What you would say in physics, it's subject to the electromagnetic force. Those are two qualities, properties of the electron. Its mass, how big it is, and its charge, that it relates to this electromagnetic force. It interacts with light. But besides these two qualities, there's also quantities. So for example, how big is its mass? Is it very heavy? Is it light? How much does it weigh when you put it on that scale? And it turns out that that number is actually really small. When you try to put a number on it and measure just how heavy an electron is, you need a really small scale if you want to measure an electron. And that number is 9.1093837.015 times 10 to the minus 31 kilograms.
Let me interrupt, actually, just to simplify things, because that's scientific notation, and Aaron's talking scientific notation. For those of us who may not be that familiar with that, that basically means 0.00000 30 zeros 91093837.015 kilograms. That's the mass of an electron. Carry on, Aaron.
And that's a precise number, exactly measured. Not exactly like putting an electron on a scale, but something akin to that. And it's a precise measured value of the mass of an electron.
That's every single electron. That's why it's called a constant. They're constants of nature. Every single electron weighs that exact amount.
Right. That's a good point. Now, also, when you deal with the charge of an electron, again, the charge of an electron is a constant, where it's always the same for every electron. And the charge measures the strength of the electromagnetic force between two electrons, let's say. So there's a qualitative aspect that two electrons, because they have the same charge, they'll repel each other. Opposite charges attract. So an electron is actually attracted to a nucleus, which is a positive charge. But two electrons are the same charge, and in a qualitative sense, they'll repel each other. But you can ask, how much will they repel each other? How strong will be the force that separates them from each other? And you can measure that. And that's determined by something called the fine structure constant, which is a way of quantifying the charge that every single electron has. And that number is exactly, or again, measured, 137.035999139. Could be there's more decimal places after that. This is how far we've measured it. And that number determines exactly the quantitative strength of the interaction between two electrons, and it's the force, the electromagnetic force.
Don't worry, you're not going to have to remember these numbers. We're just trying to give you a sense of how strange they are. Carrying further with our analogy, we could consider the various pieces of Lego. We might say, what are the weights of these different pieces? The blue pieces may weigh 5 grams. The yellow pieces may weigh 1 gram. The red pieces may weigh 2.374672 grams. And that's the idea of the constants. We have the Lego pieces. The property of them is their weight. That's a qualitative property, but the number which measures their weight is the quantity. That's the first property. But then we could consider another property of these Lego pieces. You might notice, I'm sure you've done this when you play with Lego, certain Lego pieces, if you try to separate them, you could pull them apart very easily. But there are other pieces which you kill your fingers trying to pull them apart and wedging them in between the two. And these are two pieces, usually the smaller ones, but the two pieces connect together very strongly, and it's very hard to pull them apart. In a certain sense, you could consider this as a property of the Lego pieces, how sticky they are, the strength of their sticking together. And that could be seen as an analogy for the charge, how strongly the electrons repel one another.
Or how strongly they bind to a nucleus.
Right.
You know, once you're dealing with Lego pieces, you could also have a quantity which determines just how much it hurts when you step on one of those little pieces.
Ouch. Yes, definitely. That's another quantity. But that's not relevant to our example, so the physics.
No, but it does hurt.
Okay. Aaron, can you now turn to the third component of our discussion today, which is the idea of a theory of everything. Could you please tell us a little bit about what is a theory of everything? What is the significance of a theory of everything?
To understand what a theory of everything means to physicists, you have to understand what their goal, what their aspirations are. The overarching goal of all physics is to try to explain everything in the universe with just a few basic particles and laws. Let me quote Einstein speak about this goal of physics. In the whole history of science, from Greek philosophy to modern physics, there have been constant attempts to reduce the apparent complexity of natural phenomena to some simple fundamental idea and relationships. This is the underlying principle of all natural philosophy. What Einstein is talking about is how physicists are always trying to reduce all this diverse complexity of the universe to some simple few basic laws and particles. And the idea of a theory of everything is that if we can just narrow this down to the smallest handful of particles and laws of physics, we could in theory explain the rest of the world, because by explaining these particles and the laws between them, we can understand how atoms and molecules emerge from the basic interactions between these fundamental particles. And by understanding how these molecules and atoms interact, we can understand how they come together, how they might form stars and planets, and ultimately galaxies. And in theory, not in practice, but in theory, if you really understood fundamental physics and the basic particles and laws, you in theory could explain everything else in the universe, which is just a logical consequence of applying these laws to these particles and extrapolating the consequences that derive from them. In practice, this is very difficult, if not nearly impossible, but at least in theory, if you understood fundamental physics, you can say in a certain framework, you have a theory that explains everything in the universe. And that's the true goal of physics.
Okay, Aaron, could you please give us an example, maybe one example in the framework of particles and one in the framework of laws, of what exactly you mean where you're unifying and simplifying all these diverse components into basic particles or basic laws? Could you please give an example of each of those? I think it will help our listeners.
Okay, sure. Something we've already been discussing is how if you look at a star and you look at a person, they look very, very different. One of the shocking findings of modern physics is that people and stars are made up of electrons and protons, neutrons, the constituents of atoms. Happens to be a proton, which is the center of an atom. It's not fundamental. It turns out protons and neutrons are both made of quarks, other fundamental particles, which is kind of interesting that the real fundamental particles are electrons and quarks. That's what makes up the atoms. But it turns out that a star and a human being is ultimately comprised of quarks and electrons. And when we try to reduce the complexity of stars and people, we're able to simplify them and show how they're really just derivatives of these interaction of fundamental particles. That's one example in the framework of particles, which we've been speaking about. Another one would be in the framework of laws. This was a famous example which gave birth to modern physics. Before Isaac Newton came around, the ancients looked at the heavens and they looked at the earth and they saw that they were governed, seemed to be governed by completely different laws. Things in the heavens went around in perfect circles. The planets seemed to orbit in perfect circles. But everything on earth doesn't seem to go in a perfect circle. It seems to fall in a straight line towards the center of the earth. Those seem to be completely different laws from each other. What Isaac Newton did was he showed how you could truly unify those two things, and how both of those are consequences of a universal law of gravitation, and how gravity, the force of gravity, is responsible for both the apple falling towards the earth and the moon going around the earth. Both of those things, while one's a circle and one's a straight line, are actually consequences of the same fundamental law of gravity. And this process of simplification and unifying different things which seem to be so different from each other has characterized the entire scientific endeavor throughout the past few hundred years. These are two examples, but there's so many more of how this has been one of the primary characteristics of the path that physics has used to delve deeper and deeper into the true reality behind our universe.
That's what Einstein meant when he said this is the underlying principle of all natural philosophy. Natural philosophy is the name that they used to call physics, philosophy. Back then, they didn't differentiate between these two studies. But the point is, this is an old idea. The idea of unification, simplification, is the foundation of science for as long as it's been done.
And that's why physicists have this belief that if they just keep pursuing this path to its ultimate conclusion, they're going to arrive at some ultimately beautiful, unified, simple law of nature, of physics, that's going to explain everything else in the universe. And that's what drives them, and that's what motivates them. That's the ultimate goal that physics is pursuing.
Let me explain this idea of unification through another analogy. Imagine you have a system which has a code of morality. And a code of morality might be composed of various laws. You might have one law which is you're not allowed to steal. Another law which says you can't charge interest more than 20%. Another law might say you have to give 10% charity to the poor. Another law might be you can't slander other people. You could imagine tens of such laws, and you could have one code of morality which is a list of all these different laws. But when you think about it, you may realize that there's so many laws, but perhaps we could unify these laws. Perhaps we could find that the diversity in all these laws maybe are really expressions of some more simple principle, some more simple law. After thinking it over, perhaps you'll come up with something like, treat your neighbor as you'd like to be treated yourself. This one law, treat your neighbor as you'd like to be treated yourself, is one simple, intuitive law which resonates with us. And if we think into it, we could realize that all the rest of the laws of our code of morality can be seen as consequences of this one law. For example, you can't steal. Well, that's treat your neighbor as you would like to be treated yourself. You wouldn't like someone to steal from you. You can't charge interest more than 20%. You may say, I wouldn't mind being charged interest, but too much of it is unethical. I wouldn't like that. Treat your neighbor as you'd like to be treated yourself. Give charity, 10% to the poor. If I were poor, I feel like I'd want people to help me out. Can't slander others. Treat others like you would want to be treated yourself. And the idea is that there's a unification. Though this moral code has many, many principles, many laws, we could unify them all into one law, treat your neighbor as you'd like to be treated yourself. In some sense, that's what physicists are trying to do. We study the universe, we see all different types of interactions. We see the moon going around in a circle, and we see items on Earth falling down, and we're looking to find the unification. We're looking to see how they could all be expressed as instances, applications. They could all be derived from one set of laws. That's what physicists are doing when they're looking for a theory of everything. They're looking to unify all the diversity in the universe into as few laws as possible. At best, if they could find one law, that would be great. There's a book written actually by a famous physicist, Steven Weinberg, called Dreams of a Final Theory. And physicists call this quest, this dream to find a theory, a final theory, which is a theory which would explain all the particulars, everything we see in our universe in terms of one underlying theory.
That's a beautiful analogy, Ellie.
Aaron, could you tell us a little bit about how successful physicists have been at finding such a unified theory of everything?
On an objective plane, they've done great. They've done amazing. They're really honing in on it, getting closer and closer. And one of the great accomplishments of the scientific endeavor is just how close we are. But on the other hand, there are a few hurdles that remain, and nobody really knows if they're surmountable or not. One of them is trying to unify quantum mechanics with general relativity. Remember, quantum mechanics was telling you about the rules of how these particles interact, and general relativity tells you about space and time, the framework in which they interact. Scientists have been unable to really unify those and show how they really derive from one common underlying theory. The other problem, major hurdle, has been the constants of nature. How to explain the constants of nature and the tremendous challenge they pose to the quest for finding a unified theory of everything. And that is something that we are going to discuss in our next episode.
Before we go, I've got to ask the question that every listener is probably wondering. While this is certainly interesting physics, our goal here has been to show how the deepest ideas of physics point towards the existence of an intelligent cause. But I don't see how this has anything to do with God.
Patience, Ellie, patience. We're on our way to God. First, we're going to have to understand the great mystery of the constants, the solution of which leads directly to God. Today we did all the hard work so that next time we can see the immense challenge the precise values of the constants present to physicists' dream of finding a theory of everything.
Okay, so let me summarize what we've covered today. First of all, we've explained the idea of fundamental physics, understanding the roles of fundamental particles and fundamental laws. Secondly, we've introduced the idea of constants of nature, specific numbers which are built into the fundamental particles and laws of nature. Thirdly, we've explained physicists' dream of finding a theory of everything, one set of laws which explains everything in our universe.
With the knowledge of physics we've learned today, we're in a perfect position to understand and appreciate the great mystery of the constants. Until next time, I'm Rabbi Aaron Zimmer.
And I'm Rabbi Eli Fader. and this is Physics to God.